For this video, let us try to find the number of prime numbers. Let me redo this one so that it will not be confusing, because the term is inclusive. We'll be having here from 1 to 48 inclusive. Of course, we can use the previously discussed sieve or Eratosthenes to identify here. But let's try to use the concept of our generalized principle of inclusion exclusion as to the rationale as well of including this in this playlist or in this chapter. So we're trying to determine, so we're going to have here, let S be the integers 1, 2, 3 until 48, again inclusive, and we'd like to identify the number of prime numbers there. Now take note, if we're talking about the GPIE, okay, we have the E of M is actually equal to the omega of M plus, sorry, that was minus M plus 1 combination M omega of M plus 2 minus M plus 2, sorry, that's 2 combination M omega of M plus, sorry, I am very sorry for this, is actually plus 1, here is plus 2 minus until plus negative 1 raised to Q minus M, then your Q combination M, and you will have here omega of Q. This is the generalized principle of inclusion and exclusion. So we're going to use this here, but when we use that, we need to identify the omegas of M, okay, and what would be the appropriate M that we're going to use here. So it depends on our situation. Let's talk about the number of possible prime divisors for our N, which is 48. Our N is 48. So how many prime divisors are there? In our number 3, there is a concept that we have going to take square root of N. So this is approximately, you take the square root of 48, that's approximately 6 something, okay, 6.92, so on and so forth. So this is approximately equal to, that would mean the prime numbers or prime divisors of 48 would be numbers less than 6, and those are actually 2, 3, and 5. These are the prime divisors not exceeding this square root of N for our 48. And what does this stands for? This would be our idea for our P sub 1, P sub 2, and P sub 3. That is because if you're going to return to your omega of 1, we are going to add, okay, we're going to add all the results for all P sub i's, meaning we're going to take the cardinality of each set having one of this, exactly one of these properties, and we're going to add them. As for our omega of 2, it would be the pairs, okay, so you will have this notation here, the summation of all omegas of your P sub I sub 1 and P sub I sub 2, meaning the pairs of relationships, and of course omega of 3 as well for the 3 groups. So that would mean we need to identify first our P sub 1, P sub 2, P sub 3, and then we're going to attack it differently as we're going to solve for E of 0 the other way around. Okay, let's talk about this one. What if our P sub 1 is the characteristic of all numbers that are divisible by 2? All numbers in set, let's say, where X is an element of your S. All numbers, okay, the characteristics here are all numbers divisible by 2. Here, all X's divisible by 3, and all X's divisible by 5. This would mean that if we're going to compute all of this, the numbers that represent this together with the sum of all of this here are actually no longer prime. Because if they are numbers that are divisible by 2, 3, and 5, or even the combination, then they are composite. This is where E of 0 will come in, because E of 0 we talk about having none of these properties. That is why we will be solving E of 0, and this will tell us the number of prime as we look into the opposite aspect of the computation. Hopefully that's clear. Again, you can use a sieve here, even count it on your own, but this is just an illustration using the GPIE, which will also be applicable to another problem later. Okay, so for this, let's solve first, because E of 0, the formula will be shorter. E of 0 will just be equal to omega of 0 minus omega of 1 plus omega of 2 minus omega of 3. We will end up until 3 because there are 3 of them. If omega of 3 stands for the number of elements that possess the 3 characteristics. Okay, so with that, it's even shorter if we're going to use E of O. Because if we're going to stick with this, it's okay. You can do that. But of course, you're thinking about the possibility of duplicates as well. Because if you're going to include here M, which stands for 1 and 2 and 3, we will subtract still later, and this is a very complicated, not necessarily very complicated, but it's even complicated than this formula here. So let's try to look at the omega of 0. Omega of 0, as always, stands for the cardinality of our S, and that's actually 48. Always. We have 48 integers as indicated here. Now, let's talk about omega of 1. What are those cardinality having exactly one property? So for that, let's try to solve first for the divisibility by 2. Okay, for our 48, so that's the floor. We used this before. 48 divided by 2, so the floor for that is 24. Okay, so floor function for that, that is for exactly a property divisible by 2. You have divisible by 3. That's actually 48 divided by 3. Again, that's exact 16. And if you have here, sorry, this should be cardinalities. Sorry for that. Cardinalities. Okay. You have the cardinality of D sub 5. You have your 48 divided by 5. So that's not actually exact. But since we're using the floor function, you have here 9. What are these then? These are your individuals. So this is your omega of P sub 1. Okay, omega of P sub 2. And omega of P sub 3. So your omega of 1 is actually the sum of these 3 because they are the individual results for the cardinality of a specific set for elements having exactly one property. So you have here 24 plus 16 plus 9, you will get 49. So you can see there are 48 only, but there are 49 because some of them are counted multiple times. Hence, let's proceed to omega of 2. So we have here omega of P sub 1 and P sub 2. That's actually the divisibility of 2 intersection 3, which stands for the divisibility of 6. So the floor function now, we 48 divided by 6. That's exactly equal to 8. Next, for the omega of P sub 1 and P sub 3, that's for the divisibility of 2 intersection divisibility by 5. That's divisibility of 10. For the floor function, that's 48 divided by 10. Obviously, that's 4 in the floor function. Then you have here, for P sub 1, P sub 2, and P sub 3. So you will have here, D of 3 intersection divisibility by 5. So the cardinality for divisibility of 15. You have 48, and then 15. Obviously, that's actually a 3. So all of this will comprise with the omega of 2. You have 8 plus 4 plus 3, which gives us 15. Now, how about omega of 3? Do the cardinality for P sub 1, P sub 2, or P sub 3. That's actually equal to the cardinality of divisibility by 2, intersection 3, intersection 5, divisibility of, that's 30. Alright, that's 30. So the floor function of 48, sorry for this, 30, sorry for that, 1. So this is just equal to 1. With all of this already identified, we can now solve for our E of 0 as the idea for the primes, because when we talk about E of 0, this means having, again, none of the properties, meaning they are actually not part of the divisible by 2, divisible by 3, divisible by 5, and if they are not divisible by 2, 3, and 5, below 48, then automatically they are actually prime numbers. So our here, this result, let me use red here, that's actually 48 minus 49 plus 15 minus 1. That's actually, okay, plus 15, which will give us a result of equal to 13. Okay, but this is not yet the total. Yes, these are number of primes as mentioned here, but in the process, the 2 3 and 5 prime numbers earlier were removed as they are counted, say for example here, they are counted in these portions, so they were removed from 48 as well. And then since they are prime numbers, we're going to return them, that one, and we're also going to subtract another number, we're actually equal to 1 because it's not a prime number. This is the result 13 using the GPIE, but the 3 of them will be included because they are counted, or they were also removed. And the subtraction of 1, since we were not able to remove 1 earlier because 1 is actually a non-prime as well. So you will get a result of 16 minus 1, you have 15 prime numbers. All in all, less than 48. So there are 15 prime numbers, and we did this using the GPIE, using the concept of E of 0. Now, if you're not convinced with this, let me return to the previous page. This was our result early in the previous video when you talk about the sieve of Eratosthenes, talking about the prime numbers between 1 to 100. So 48 is somewhere here. You can see 48 is somewhere here, right? This is where 48 is located. So how many prime numbers are there? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So less than 48, there are really 15 prime numbers. As checking, you can do this one, but if you are tasked to use GPIE, you will be using this as part of your process. Thank you very much for watching.